Given a cone and a cylinder that share the same base and height, we'll show that the volume of the cone is a third of the cylinder. We'll use a proof by contradiction for this one and assume first that the cone is less than a third of the cylinder. We're going to use the trick that we used in proposition 12.2, where we approximate the cone with pyramids and the cylinder with polygonal prisms. We'll start by inscribing a square in the base. In proposition 12.2, we showed that the square is greater than half the circle, so that the difference between the circle and square is less than half the circle. From the square, set up a prism of equal height with the cylinder, so we are approximating the cylinder with the prism. Let's now show that the prism is greater than half the cylinder. Circumscribe the circle base with a square and set up a prism of equal height. Then, since our two prisms are parallelopipeds of equal height, the circumscribed prism to the inscribed prism is proportional to the circumscribed base to the inscribed base. The circumscribed base is twice the inscribed base, as we've already shown, so the circumscribed prism is twice the inscribed prism. The cylinder is less than the circumscribed prism, so the inscribed prism is greater than half the cylinder. Back to the base. Now construct an octagon. As we saw before, the difference between the octagon and the square, this region, is greater than half the difference between the circle and the square, this region. Take these triangles and make prisms just like we did with the square. Now we'll show that these octagon prisms are greater than half of the difference between the cylinder and the square prism. To do so, draw rectangles on the base as so, just like we did before, and make prisms out of those. The octagon prisms are half of these rectangle prisms, and these portions of the cylinder are less than the rectangle prisms. So the octagon prisms are greater than half of the difference between the cylinder and square prism. We can do this same process, approximating the cylinder more and more finely, until the difference between our approximation and the cylinder is smaller than the difference between the cylinder and 3 times the cone. Let's assume, for the sake of the argument, this happens at the octagon stage. Then the octagon prism is also greater than 3 times the cone. But by proposition 12.7, the octagon prism is triple its octagonal pyramid, so that the octagonal pyramid is also bigger than 3 times the cone. But the octagonal pyramid is inside the cone, so there's our contradiction. Thus the cone is not less than a third of the cylinder. Let's now assume the cone is greater than a third of the cylinder. Like we just did, inscribe a square and make a pyramid out of it, and then do the same with an octagon. And for the same reason as we've just seen, we can approximate the cone more and more finely with pyramids until the difference between the cone and the pyramid is smaller than the difference between 3 times the cone and the cylinder. For the sake of the argument, say this happens at the octagon stage. Make a prism of the octagon base. The pyramid is a third of the prism, so the prism is bigger than the cylinder, but it's inside the cylinder, so it's smaller than the cylinder, and there's our contradiction. Thus, the cone is not bigger than a third of the cylinder, and is thus a third of the cylinder.